Now tell me if you could see this. Okay, now let's start it. So in the last few classes, what we did, we read in detail the PMMC instrument, and I said that is you read Sahani for that. That is a very good book, and every aspect of the instrument is covered in very detail. So I tried to cover it with examples and a lot of time it's spent on it. Now we'll move to another instrument, another type of instrument which we call the moving iron instrument. Okay, fine. So now which we call as a moving iron instrument. So what we read in PMMC instrument is that that instrument is only for DC and to measure the ammeter, voltmeter and all those things for DC. But moving iron instrument is for both AC and the DC. That is one big advantage that you can measure AC also. And another difference you can see that in galvanometer or PMMC instrument, the current which can pass through the instrument is very small. I said in the order of in milliampere, 2 milliampere or 10 milliampere or so. But here if you see that the current which could pass through the instrument is not that small. It could be very high also. In fact, 100 ampere current may pass through the instrument. So this is a very big difference between the PMMC instrument and moving iron instrument. You should remember this. Now, if we come to the construction of moving iron instrument, there are two different types of moving iron instrument. First one is attraction type moving iron instrument, and next one is repulsion type moving iron instrument. So based on the construction and the type of operation, these two main classification we can say. One is the attraction type moving iron instrument and another is the repulsion type moving iron instrument. Now the current to be measured in general is passed through a coil of wire in the moving iron instrument. So generally the thing is same as the current will pass through a coil of the wire in the moving iron instrument. So in case of voltage measurement, we will mark the scale as a voltage. But the thing is that the current will pass and deflection happens. The voltage measurement, the current which is proportional to the voltage will be measured, and obviously we will mark the scale in voltage. And there are also in construction you will see that there is a number of turns of the coils, and upon the current to be required to be sent, and the current will pass through it and it will be magnetized, and there will be iron which will be attracted and move, and there is a either attracted or repulsed, and there is a deflection pointer which will be deflected on the scale. So if we come the two specific things, one is the attraction type and another is the repulsion type. So let's come to the attraction type. So attraction type moving around instrument is shown in the figure. In the figure you can see the C is pointed as the coil winding. So coil will be on, and you will see that there will be a moving iron circular things, and there will be a controlling weight W1, W2, W3. And another thing you will see there is a chamber where the piston will move inside the air. So it becomes a air damper. So air damping is there, and there will be a pointer which will be moving over the scale. So in the attraction type of moving around instrument, So it depends on the attraction of an iron vein. You can see that the iron vein, which is written as the moving iron, that is the iron vein. So into a coil carrying current, so there will be a coils which will be carrying the currents, where the voltage is to be currents. So once the current will pass through the coil, the so the instrument in moving around instrument there will be a magnetic field, and the iron vein, which is shown as D, is will be attracted. Now once the iron vein is attracted, there two opposing force will come into play. One is the damping, which is the piston in the damping air chamber, and another will be the spring. There will be a spring which will give the restoring torque. So when the current to be measured is passed through the coil C of the coil winding, it is written, a magnetic field is produced, and this magnetic field will attract the iron vein, or there will be eccentricity where it will be attract the iron vein spindle towards it, and the spindle is supported at the two ends on a pair of jewel bearing. Thus when this will be attracted, the pointer will move over the scale, and the scale is calibrated so that the pointer is shown the voltage or current of of um, the current that will passing through the coil winding. So this is the main construction. So let me tell again. So there will be a coil winding through which the current will be passed. So here you see that the coil winding, as the current will pass through the coil winding, and it can be very high in nature. There is no limitation. You can increase the gauge of the coil winding, and the more and more current can be passed. And once the current will be passed of the coil winding through the coil winding, the area will be magnetized, and there will be iron vein. The iron vein will be attracted. Once the iron vein is attracted, there will be a spring which will be producing the restoring torque. There will be a damper, air damper, which will be producing damping, and at some point of time, the pointer will be it will be equilibrium, and it will deflect it at some angle and then stay there. And with that, what will happen, the pointer will deflect it over the scale, and once it is deflected over the scale, you can read the scale and you can tell that okay, this is the reading once you calibrated the scale. So, so more and more if we go, it's operation is very simple. The control torque will be provided. So deflecting torque will be provided by the magnetic field, which attracts the iron vein. The controlling torque will be provided by the two hairspring. So here it is not shown in the figure, the hairspring, and hairspring will be there, and mm, similar to PMMC instrument. Okay, but one main difference is that in PMMC instrument, you see that the hairpin itself is carrying the current, but here hairpin will not carry the current. Here the uh, coil will carry the current, and the moving vein is attracted, and this vein will be on a spindle, and spindle on the two sides of the spindle there will be two hairspring. Once the spindle is attracted, the hairspring will provide the control torque or restoring torque, and there will be no current carrying part through the hairspring. So damping torque is provided by a thin vein or thin piston in a closed shaped box, and where the only air is there, so air friction damping is there only. Also, the eddy current damping cannot be used here in excuse me, in MI instruments, because the fact is that any permanent magnet will be required to produce eddy current, but here there is no permanent magnet, only the current carrying coil is producing the magnet, so there will be no eddy current damping. This is another major difference between the PMMC instrument. Now you think about how I am saying that it can measure the AC and DC both. So suppose the current in the fixed vein is reversed. In the current in the fixed vein is reverse, but whatever be the current of the fixed frame is reverse, the field of the magnet produced is also the reverse. The polarity induced on the vein is reverse. Thus, but the magnet will be produced and the attraction will happen. Thus, whatever be the direction of the current in the coil, vein is always be magnetized in such a way that it attracts the coil and the coil will be attracted, and similarly the deflection over the pointer will happen. So at least in attraction type, you see the few things which are to be remembered. First thing is that there is no permanent magnet. Second thing is that there are coils which carries the current and produce the magnetic field. As the coil carries the current to produce the magnetic field, so current should not be very less, which is passing through the instrument. The current could be very high and it could be as high as 100 ampere also. Only thing that you have to make sure that the wires which is used to own to produce the magnetic field can sustain that much current. Next thing is that the moving part, here the moving part is iron vein. Once the magnet is produced, the iron vein will be attracted and there will be damping and there will be a two spring which will produce the restoring torque or controlling torque, and ultimately an equilibrium is achieved and the pointer will deflected, and we can see the pointer on the calibrated scale to take the readings to know that what will be the values of the current and subsequently voltage also if we want. And another major difference is you see that moving part is not carrying the current. So the spring in PMMC, springs are carrying the currents, but here no current will be passed through the spring. So as the moving part is not carrying the current, so the current could be very high, which you could send through the moving iron instrument. Okay. And here you see the as the direction for AC current, as the direction is reversed, still there will be magnet produced and attraction will happen, and if the attraction is happened, still the pointer will be deflected, and as a result it can measure both AC and DC currents. This is all about the attraction type. So now let's see if you have any query, otherwise I will go to the repulsion type instrument. Okay, there is no query as such. So then let's move to the repulsive instruments. So moving iron instrument repulsion type or repulsive type, we can say repulsion type, we can say. So we can write is repulsion type. So moving iron instrument repulsion type. In the repulsion type instrument, there are two vanes, as you see in the figure. There are two vanes uh, inside the coils. So one is fixed vane, and another is movable vane. So the current carrying coils are wound in such a way that the both the magnet produced in fixed vane as well as the moving vane will be in same polarity, and they are repulsive in nature. So you can see that two figures are there. One is radial vane type, another is coaxial vane type. Whatever be the case, in this case there will be two vanes inside the coils, and coils will be wound on the two vanes. Same coil. Here also coil, you can see the spindle. So in the coil, in the spindle there is one vane and another which can rotate, and there will another vane which is fixed, and there is a coil which is wound on the two vanes. So once the coil carries the current, then the magnetic field produced on the two vanes, and the magnetic fields are produced on the two vanes in such a way that both the fixed vane and moving vane have the same magnetic poles. And they will be deflected. As the deflection force comes, or they will get repulsive force. As the repulsive force come, fixed vane cannot move, but the movable vane is free to move. So once the movable vane is free to move, it started moving over the spindle, and a spindle is attached on the moving vane. So spindle moves. There are springs on the top and bottom spiral things. So once the spindle moves, the spiral spring get start producing the controlling torque, and once the controlling torque is equal to the um, deflecting torque, which is produced by the repulsive force of two magnets which are produced by the current carrying coils, what will happen? The spindle will not move further or not rotate further, and a pointer is attached with the spindle. So as a result, what will happen? As a pointer is attached with the spindle, pointer also it get deflected, and at the equilibrium point it will remain fixed, and that deflection can measure over the calibrated scale to know the current or voltage of the circuit, or to know the current passing through the coil. That can be later, if you want, can convert it into the voltage. So this is the main construction of the repulsive or repulsion type instrument. So again I am repeating. So in the new figure you may appreciate it. Here you see, so you see that there are two NS you have seen. So there are two vanes, and there is a coil field. You can see on that coil could be owned, and once the current passing through the coil, these two vanes produce the same magnetic field, and as the fixed vane cannot rotate, the moving vane start rotating. As it start rotating, you see the spring control on the top. Spring started producing the restoring control or the control torque. As a result, the pointer start moving. At equilibrium, the pointer gets deflected, and the spring torque is same as the deflecting torque, and at the same time pointer gets deflected and stay on the deflected position. You can read that position over the calibrated scale, and you can measure the current flowing through the field, flowing through the uh, coil, which produces the field of the magnetic field. So now the right hand side instrument, you can also see this is more realistic. Although something is wrong, you see on the left hand side there are two circles. One is the fixed vane, and inside circle is the moving vane, and they are with the same center and with the less radius, and always equal gap. And this is not the case in reality. I'll show in another figure. So here you don't mind this gap. This gap is somewhere less, somewhere more it should be, but here you see the gap is same. It is not the case. So you see that there is one circle, or which is fixed vane, and there is another circle which is a moving vane. Gap you don't mind, I will tell how the gap will be. And now you see there is a fixed vane, there is a moving vane, and there are the wires wound on the two vanes, and there are springs on the spindle, and the moving vane is attached with the spindle. As the current pass, two vanes produce the same similar polarity of magnetic field, and they started repulsive. They get repulsive force. As the moving vane can repulse, can move, so it started rotating. This spring started producing the controlling torque, and at one point of time it has the deflecting torque equal to controlling torque, and the deflection gets stopped, and it get deflected and stay there, and deflection is proportional to the current passing through this coil. Now here you see that more realistic figure. Left hand side, if you see, you can see the moving vane inside, you can see the fixed vane outside, you can see the current carrying coils. So in the left hand you see the more realistic cases. Okay, so you see that the fixed vane is there, and then moving vane, this is what I want to say, the moving vane inside, and you see that moving vein and fixed vein gap is not uniform. Here you see, I will come why it is not uniform, but at this point you just remember that it is not uniform because here the gap is very small, here the gap is very large. It is intentional. I'll tell why it is done so. But for the time being, you noted that in repulsive type, there are two veins, which is fixed one, another is moving one. Moving one has a different gaps at different angles, and there are coils. There is a coil which is wound on the fixed vein, and as the current passes through the coil, both the veins, moving vein and the fixed veins, are magnetized, and moving vein moves, and then spring started expanding, and it produces the torque, and ultimately pointers it deflected and stay there at equilibrium point. If you see how the instrument look like, it's kind of a box. So this type of box you have seen in your machine lab, you used to carry the box with this handle and attach the um, wires with this meter. And if you see this is a voltmeter, and then you see there is a small pointer, there is scale. This is, oh sorry, there is a pointer, there is a scale, and you have seen that there are two, one for DC and one for AC, and you have to make it either it is a voltage, you can measure the voltage, you can measure the current, and you need to keep this in the proper range so that your uh, deflection will become proper in this range. Okay. So another thing I want to say, in the top one you see that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is uniform scale in, but the bottom one, the scale is not uniform. 0, 10, 20. This you just noted. Now will not explain. Later we'll explain. But the scale on the top is the voltage or the current, and below one is the resistance. Now the last figure, maybe yes. So here it is quite nicely shown that the moving coil and the moving vane and the fixed vane and the spring, okay, and the damping vane and the scale and the hairspring and all those things. Now here, so if we go to the repulsive time instrument, there are two types mainly, radial vane type and coaxial vane types. So in radial vane types, here you see this one. So here the vane, you see that this is the coil, this is the fixed vane, this is the moving vane, and you see this is the not the coaxial. So this is called the radial vane, and this is the coaxial vane, where the two vanes are in the coaxial. This is more popular coaxial vane. So that's what I mentioned here. So there are two types of repulsive repulsion type instrument. There is a radial vane type. In this type, the vanes are radial strips of iron. The strips are placed within the coil as shown in figure 2.5a. The fixed part is attached with the coil, and the movable one is attached with the spindle. The current flows through the coil, and the generated magnetic field are the same. They get repulsive force, and the moving coil get deflected till it is the deflection is the same as since till the controlling torque is same as the deflecting torque, and it get the deflecting angle. Now, if you see the coaxial vane, that's the many figures I showed. This is most popular. So, in this type of instrument, moving part and the fixed part are the coaxial, circular coaxial cylinders. Although the not coaxial, although the gaps between the two cylinders are not same at each point. So that's what I emphasized. Current when passes over them, it produces the magnetic field. Both are the same polarity, and then it gets the deflection. The moving spindle moves, and the same thing equilibrium happens with the spiral spring, and you can read the angle theta in terms of ampere or voltage. Now here one thing in the moving iron instrument, it is that the instruments are said to follow the square law. Okay, it is not the proportional, that I will come. This is another major thing that I will come in the next slides. So, but till now, let me ask you whether you have understood the construction. So, I try to explain the construction in very detail. What are the different types of construction, how they are constructed. Now, you tell me that you have understood the construction of the instrument, or you have some queries on the construction of the instrument. Now you can tell me. Okay, as none of you is speaking or writing anything, so I assume that you have understood everything properly, whatever I said. Then let us proceed further. So now torque equation of a moving iron instrument. As we have seen the torque equation in PMMC instrument, the similar type of torque equation in moving iron instrument we need to deduce. So to deduce the expression for torque of a moving iron instrument, we need to do the energy balance, energy relation between the different types of elements and the spring constant, controlling torque and everything. So at the mechanical work done, what will be the mechanical work done? It will be stored as energy, that is the torque multiplied by the angular deflection. So at any point of time is d theta is the angular deflection and torque is the TD. TD is the deflecting torque, which is produced by the repulsive force among the two magnets. So the total work done will be TD into d theta. So due to the change in inductance, there will be a change in the energy stored in the magnetic field. So let I be the initial current, L be the instrument's inductance. There will be coil, so inductance will be there, and as the AC current is there, we need to take it into account. And theta is the deflection. So if the current is increased by dl amount, then it causes the change in the deflection is d theta amount, and the inductance by dl amount. So in order to involve the incremental dl in current, di increment in current. So if the current increment is di, change in inductance may be dl, and the change in theta may be d theta. So now we can write the applied voltage must be increased by E is d phi d theta. Phi, you know the flux produced, it is Li. So ddt of Li. And here you see as the part is moving, so inductance is not constant. This thing you should uh, remember, or you should mind it, that as you see that there are two veins, one vein is moving, and there are the different types of instruments and positions, and there it is changing the air gap and all. So you can see that L is not also fixed, so we can write E is equals to d phi dt, and phi is Li, so d dt of Li, and you can write I dl dt plus L di dt, and the electrical energy supplied is EIdt. So there you can write E is IDL multiplied by I, so I squared DL plus IL dt, IL di. So that we substitute here, this one. Okay, so this one we substitute. Dt will cancel. So now the current changes from I to Di, inductance changes from L to L plus DL, and therefore the stored energy which changes from initially stored energy was half I square L, and final stored energy will be half I plus Di square into L plus DL. So half I plus Di square into L plus DL minus half I square L is the change in the energy stored. DL di is very small, so di square and dl square we neglect. So what we get is the half I square uh, plus half I square di, and it's multiplied by here L and dl, and both dl di are also neglected because both are very small, and and you see that half I square L will be cancelled out. So the remaining terms will be IL plus half I square DL. And now if these two things you balance it at the for the energy conservation, you see that I square DL plus ILDI will be equals to ILDI plus half I square DL TD d theta. So these two things, one is here ILDL plus half I square DL plus TD d theta, which will be same as the EIDL. So this one I square DL plus IL DL. You see that equation 2.9, 2.9, 2.29 is balanced with the equation. So you see that IL DL will be cancelled out. I squared DL will be half will be subtracted. So we'll get half I squared DL will be equals to TD into d theta, and deflecting torque TD will be half I squared DL d theta. So in this way we got the deflecting torque. So how we'll get the deflecting torque? That is half I squared DL d theta. That you have to remember. Now the deflecting torque produce a deflection. Here everything should be in SI unit. Theta in radian, L is Henry, I is ampere. So TD will be Newton meter. Now add the moving systems is going to deflect with the deflecting torque. This one half I squared d theta. And as it started deflecting, the spring is started giving the opposing force, which is TCK theta. And that equilibrium, we are not considering the transient, we are considering the steady state equilibrium. So at equilibrium position, Tc will be equals to Td, controlling torque will be equals to deflecting torque, and you see that the Tc will be equals to k theta, and deflecting torque is half I squared dl d theta. Both will be balanced, and from here you get theta will be equals to half I square by k dl d theta. So here what you see half is the constant, there is k is the constant, which is the spring constant. So these are the constant. I is not constant. So deflection is proportional to I square dl d theta. Okay. So the deflection is proportional to square of the current. Okay. You can say that RMS value of the operating current, root means square values of the operating current, and the deflecting torque is therefore unidirectional. Whatever be the current, I square is coming. So it is the RMS value. So it is the unidirectional. Whatever be the polarity of the current, the deflecting torque will be in the same direction, and you get the deflection of half I square k dl d theta. So you see the deflection is proportional to the square of the I square. So in if the current is DC, it is directly proportional to the square. If the current is AC, then what will happen? It is the proportional to the RMS value of the operating current. That you have to remember. So this is the case. So theta is proportional to half I square. Theta is proportional to I square dl d theta, right? And if L is not a function of theta, but many times L is a function of theta, we cannot oversimplify it. But vaguely we can say that deflection is proportional to I square. That means it is proportional to RMS value for the AC current. Okay. Now tell me any query or any doubt till this point. Okay, you don't have any doubt or any query, so you understood everything. So if even if you don't understand, you read the Sahani. This is from Sahani, mostly from Sahani, and Sahani is very nicely written. You download it, read it, you see that the same things they have derived. Now, there are the advantage and disadvantages of the moving iron instrument. Definitely, moving iron instrument is advantageous in the sense that it is very cheap and it is very robust. It is not fragile. And another advantage is it can measure both AC and DC. So the same instrument can be used. and and another thing is that is it can pass the huge amount of current, 100 ampere up to 100 ampere. So the use of the shunt or the multiplier is very limited for this type of instrument, although there are shunts and multiplier. A few times we need to use it, but the use of such in this instrument is very limited because we can pass the whole current as it can withstand. Now there are disadvantages of the moving around instrument, and we'll see how um, it can be removed. The first thing is that the deflection is proportional to I square. So I always say that if the scale is linear, so it will be very nice, and we always prefer the linear scale. But here you see that the deflection is proportional to I square. Hence, the scale is not linear. The scale is not linear, and it is the square. It follows the square law. So if it is the square, that means it is cramped in the lower end and sparse or expanded in the upper portion. And it is very difficult to see at a glance and see the meter readings from if it is the scale is square, because you will not see that the scale marked uniformly. The distance between 1 and 2 is not same as the distance between 9 and 10. So if your meter reading is in between 1 and 2, then you have to be very careful to see what is the exact reading. And if it is in 9 and 10, you also have to see the very careful that what will be the exact meter reading, because it is not the uniform. And if it is not uniform for small I, it will be cramped near. If it is the I is small, if I is high, and what the higher scale, higher range, higher part of the scale, it will be sparse. That means more expanded. So it is very difficult to get take readings for such type of scale. Now there are few more things which we need to eliminate the effects, such as the hysteresis error in the instrument, as there is no permanent magnet. The magnet is being produced, and the current produced in the two directions. There are residual magnetic fields, and which produce the hysteresis effect. And hysteresis effect, it may be minimized by using the veins of nickel iron alloy, which has the very less hysteresis effect. So that can be used. Now, when used for measuring, the reading values may be affected by the variation of the frequency. It is another issue. So when we call the DC, there is no concept of frequency, but when we are measuring AC, there is a concept of frequency, and all the inductance values and all the reactance, everything depends on the frequency. So we need to take care that what is the frequency we are going to apply. So that is very crucial issue when you go with the measurement of AC parameters, AC current, AC voltage. So when you use the measuring the AC, the readings may be affected by the variation in frequency due to the change in the reactance value of the coil, which has some inductance. Okay, so with the increase in the frequency, the iron losses and the coil impedance increases. So whenever you try to measure the current and the voltage, always you need to see what is the frequency. And later we will read that for some part of the or range of the frequency, it is fine, and if it goes beyond some range, it is not possible to use moving iron instrument, or we need to build a special moving iron instrument or take some precaution. That we'll discuss in a later stage. For the time being, you should know that for the timing, you should remember that this, as the AC current, there is a component of frequency, and you need to take care whenever you are measuring AC current. You need to note what frequency, tentative frequency it may be, and based on that you need to see whether your meter is capable of handling that frequency range. If yes, you can use that meter. If no, then you have to think what you can do, because with the frequency, the reactance of the coil, okay, and the inductance, everything depends. And based on that, sometimes, particularly I'll tell, particularly at very large range of frequency, this moving around instrument becomes useless. You need to have some different mechanism. Now another thing is that, as I say, that there is a huge current, 100 ampere, still 100 ampere current can pass through it, because the coil which is passing, it is producing magnetic field, and it is not the moving coil. So, but that at disadvantage, the shunt is not that much essential. Multiplier is not that much essential, but there is disadvantage also because as if if large amount of current passes, the power consumption is very high. I squared R loss will be very high, and ultimately, and magnetic losses in vein also very high. Okay, and the instrument is no longer a very sensitive instrument because you need large power, large current to pass. So the sensitivity, if I ask the sensitivity of the moving iron instrument and PMMC instrument, which is higher, definitely the sensitivity of PMMC instrument is much higher than moving iron instrument, as it takes very small current and get very huge deflection. Here you need to send a huge amount of current in order to magnetize the magnet, not the permanent, magnetize the iron core and all. So, and as a result, you will get huge loss, I square R loss, and that is not desirable because our main principle say that when you want to measure something, we should not have introduce a meter in the circuit. The meter should not introduce a loss so that the overall full character of the circuit and full character of the systems is changed, or the loss happens in meter. That should not happen, but that is very rarely things you can do in moving around instrument because a huge current pass through it. There is I square losses is there, hysteresis losses is there, and magnetic losses in the veins it happens, and this instrument is not very sensitive. Now let's see if you have any query till this point. No, it's 50 already. Okay, you are not saying anything. Hope you understand everything. So now, tomorrow, what about tomorrow 9 to 10 class? So tomorrow 9 to 10, is that fine to all of you? Only one class I want to take. Please respond. Okay, fine. So then tomorrow 9 to 10 a.m. we will be coming to our next class. And one thing I was telling repeatedly today also, I want to say that you read Sahani for these things and try to solve all the examples and try to solve um, all the exercise problems. Okay, Sahani is a very nice book. Everything is written there. I am following Sahani and try to solve all the examples given there. Questions will come from those examples. Okay. So today we could end here. So we read lot of things. We read the construction of the moving iron instrument. There are different issues. What is the expression of the moving iron instrument during the deflection and all, and how the scale will look like. It is not a linear scale. What are the different advantages, disadvantages? What are the different type of construction? Everything I tried to explain in very detail. So now today we will end here, and tomorrow again 9 to 10 I'll come and discuss on it, and we'll discuss further on moving iron instrument, and then gradually we'll move to electrodynamic in electrodynamometer, or which is also a transfer instrument. We'll move it, we'll discuss it in detail. So now today we end the class here, and thank you for attending the class, and now have a nice day. Thank you all of you. Tomorrow we'll meet again. Okay, thank you, have a nice day.